First, minimize the perimeter by getting the measurement of the rectangle, which is x plus x and y plus y. That will make it 2x plus 2y. So in this case, we will get the derivative of 2y. When the constraint of the area is equals to 1000. And the area of the rectangle is x times y. That I'm going to derive to be a single variable. So I'm going to divide both sides by x. And that will be 1000 divided by x equals to y. So I'll put that back in, and that will make 2x plus 2 times 1000 divided by x. And we will just simplify this, and the answer will be 2x plus 2000 x raised to negative 1. And we will just derive 2x plus 2000 x raised to negative 1, and the answer will be 2 minus 2000 x raised to negative 2. And the critical members of the equation. So it will be 2 minus 2000 divided by x squared. So when finding the critical members, I always group them into a single fraction. That is why I came up with the equation 2x squared minus 2000 all over x squared. So for this equation, you will get 2x squared minus 2000 equals 0. And if you transpose 2000 to the other side and divide both sides by 2, you will get x equals 1000. So finally, x and y will become square root of 1000. That is why the rectangle is actually a square, because y is equals to square root of 1000 and x is equals to square root of 1000. First, the volume needs to be 10 meters cubed. So let us write the cost of the base, which is $10 times the area of the base, and the area of the base is the length times the width. So it will be 10 times x times 2x, and that will be the cost of the base. And the cost of the sides is 2 times 6xh plus 2 times 6 times 2x times h. We have two panels, that is why we need to multiply it into 2. So just simplify it, and you will get 20x squared plus 12xh plus 24xh. So this will be equal to 20x squared plus 36x, and this will be my cost. But we want to optimize with respect to one variable, so we have to express h. We want to optimize with respect to one variable, so we have to express h as a function of x, so that we can optimize x. To do that, we need to know that x, the width, times the length, times 2x, times the height, is equals to 10. So we just divide both sides by 2x squared, and we get h is equals to 10 over 2x squared, or h is equals to 5 over x squared. And just substitute back right over here. So our cost as a function of x is going to be 20x squared plus 30x x 36x times 5 over x squared. So our cost as a function of x is going to be 20x squared plus 180x raised to negative 1. So we finally have the cost as a function of x. So we just need to optimize. So the derivative of c is 40x minus 180x raised to negative 2. So transpose negative 180x raised to negative 2 the other side. So we will just divide both sides by x squared. So that will be 40x cubed equals 180. And divide both sides by 40, and that will be x cubed is equals to 180 over 40. Or 118 over 4, or 9 over 2. So the critical point will be 9 over 2. And if you get the approximate value, you will get 1.65. Now find the cost of the material for the cheapest container. So we only need to figure out what our cost is. So we just need to put 1.65 into this equation, and we will get 163.54. So the cost when x is 1.65 is approximately equal to $163.54. And the minimum cost to make this box is going to be $163.54.